Hello, I'm Emanuel and I'm going to present our work titled Learning a CBF Controller for Adaptive Cruise Control under Model Uncertainty. The authors are Emanuel Munoz, Ching and Professor John Dolan. Adaptive cruise control is a traditional problem in autonomous vehicles. It consists on keeping a safe distance from the front car while trying to reach a desired velocity. This problem is safety critical because in case the safe distance is not accomplished, it could provoke some collision between the vehicles. So there is a permissive solution called CBF, or control variable functions, that considers systems like x dot equals fx plus gx times u, such as for this system we can define a safe set z, as is shown in the left part of the slide, that could be defined by some conditions defining h, such as that when h is greater or equal than 0, so the system is within the boundaries of this safe set. To keep the system within this safe set, there must exist a control law u equal kx, such that h dot is greater than or equal than minus lambda times h. This lambda is a constant value. The problem is that we don't have a real model. We have an approximation that is called also a nominal model. This is model uncertainty. So specifically for adaptive cruise control, we have as an uncertainty also the roll resistance. So in our prior work, there is a solution that it's proposed, and it proposes a learning approach that collects data episodically, such that it improves the CBF controller each time more. So inspired by this work, we propose a similar approach to solve the problem of model uncertainty in the ACC problem. So first we define the ACC model, that is the one shown or expressed in the slide below, where it's important to stress the part of the friction, or also called the rolling resistance, where it's modeled as a polynomial function that depends on the velocity. And this is important because it has as a coefficients some parameters that are not always well defined. And on the other hand, we have also the same constraint that it says that we have as a distance that is set, that to be safe it needs to be greater or equal than the time look ahead and times the velocity, and an extra term that considers the maximum input of the acceleration of the vehicle. So when we refer to the episodic uncertainty learning, we're taking that we have a real model such that the h dot is equal to the expression shown in the slide. But because we don't have the real model, but instead we have a nominal model, we need to make an arrangement in the equation such that we have an expression similar to the real model, but at the same time we have a residual error that could be modeled with some estimators. And in this case we chose to try neural networks. So the strategy that we follow is that there is a nominal model that fits a control reference in a learning CBF controller that goes directly to the adaptive cruise control neural model, and from this trial or experience we collect data. This data updates the estimators such that they improve the learning CBF controller. As a result, we simulated this DSACC model, considering that the uncertainty is in the rolling resistance parameters. For the first experience, that is when we don't have any data, we can say that this is a nominal controller, and as it's shown in the plot, it breaks the safe set because it passes the safe set hx. Also, we see that as the experience are higher, the CBF is safer because it does not pass the blue line that defines the safe set. So we could say that the learning enabled CBF is safe. As a conclusion, we validate the performance of the learning enabled CBF, specifically for the ACC application. The result that we showed clearly show that the proposal reduces the error produced by the parameter uncertainty in the model, and also that because of this, the estimators converge such that it adequately compensates the model uncertainty. I would like to thank Chin Ding, Professor John Dolan, and Rich Schilbersen for providing their full support during this program, and also to the risk community for making this amazing opportunity possible, and also to the Robotics Institute of Carnegie Mellon University for sponsoring this internship. Thank you.